Got it. Okay, so if it live streams to YouTube, will it still be there after it's over?
You should have the option to save it.
I should have the option to save it. Okay. Oh my gosh. Okay, so we're live. Okay, but I'm not moving. What's happening? Okay, there we go. All right, so yeah, let's get started. So last time we were talking about divisibility. So let's write up the definition of divisibility real quick. And then, yeah, and I think one of the biggest, I was talking to a friend at a different university who teaches out of the same textbook, and she was saying the biggest shift at the beginning of this course is starting to think about division in terms of multiplication, right? So we're talking about division, but when we write things out, we write it in terms of multiplication. And that's a pretty big shift, I think, in the way that you're thinking. And that's what I keep saying in your, oh, what's happening? Oh. So that's what I keep saying in your comments is, you know, quit writing things as fractions, quit writing things as fractions. So that's what we're working on. Okay, so I feel like there's a time lag or something on this. So yeah, there's just a time lag. Okay, so that's a little distracting. Okay, so let's write down the definition of divisibility. I think I'll go back to Zoom and it will look better. No? Why can't I just watch it in Zoom? Okay. Whatever. Okay, so A is divisible by B. Or sorry, yeah. If there exists, oh, we need A and B to be integers. A is divisible by B if there exists a C and Z such that A equals BC. And we write this B divides A. So we say B divides A. So yeah, I guess what it was written in a definition is we say that B divides A if A equals BC for some integer C. So anyway, okay, so there's that. We were right here with this question. If B divides A, what can we say about? Okay, maybe I'll just make the volume go down. Okay, there we go. That's better. What can we say about the relative sizes of A and B? Or what do you think? If B divides A, what can we say about those relative sizes? You feel like A is bigger than B, right? Yeah. So we can say that the absolute value of B is less than or equal to the absolute value of A. And is that true? How can we prove that? And we could even go further because we know that the absolute value of that the actual value of B is less than or equal to the absolute value of B, right? So we could even say B is less than or equal to absolute value of A. So why is that? Well, it's going to go back to this definition that A is equal to B times C, right? So the absolute value of A is equal to the absolute value of B times, well, the absolute value of C, I guess we could say it that way, which is greater than or equal to just the absolute value of B by itself. So, so we can say this. this way, and then that's greater than or equal to the value of B. Because absolute value of B is gonna be the magnitude of B. So, so this is a fact. And we'll refer back to this later, so we'll call this a remark, maybe. We'll say if B divides A, then that. So here's our remark. Yeah, so I'll refer back to that remark in a proof later. So, but that shouldn't be a huge surprise because you divided things before, and so you've had experience with relative sizes and things. Oh, Benjamin, I didn't see you come in. That's your quiz. Okay. So let's keep going. Okay, so what do you think about, we talked about divisors. So what do you think about a common divisor? What would be a definition of a common divisor?
It would be if C is equal for two different A's and B's.
Yeah, so a common divisor would be a number like a C that divides both numbers, right? So we could say, I don't know, let's write this down. We can say that A and B have the common divisor C. Oh, and I guess I keep skipping the fact that those guys are integers. So we can say A and B elements of Z have common divisor C in Z, if and only what do you think the definition would be? What do we need to have? Well, what would C have to do to be a common divisor? Yeah. So C has to divide A and C has to divide B. Yeah. So let's write all the divisors of 12 and the divisors of 30. And then let's see if they have any common divisors. So you can work with your other people, come up with the divisors of 12, divisors of 30.
One, two,
1, 2, 3, 4, 6, 12.
Remember, divisors can be positive or negative. Yeah. Yeah, we'll write all of them down. So what do we have? Yeah, they don't have to be primes. Is that what you were talking about? There are a lot of them. No, it's not a divisor. Okay, and divisors of 30. Actually 12 will be in there. Yeah, so I guess when we were kids, we used to write them like that. We'd start on the outside and then go in, right? Remember doing that way? Yeah. Oh, I guess. Okay, and then let's circle the common divisors. So what are the common divisors here? Well, 1 is 1, right? What else? 2, 3, not 5. 6 is 1. And that's it. So those are the common divisors of 12 and 30. Okay, and then we're about to introduce another concept, the greatest common divisor. Okay, so how can we define that? The greatest common divisor of integers A and B is the number, the integer D that has the properties. How did I write it in my notes here? I feel like I'm rambling. Yeah. Oh, so I guess we have to say that A and B are not both 0. Integers A and B not both 0. And is the largest integer D that divides both A and B. So here's a question. Does D have to be positive? Does it? Yeah, why?
Because like they'll have the positive and negative, it's both factors, so positive.
Okay, what do you think? Yeah, so if D divides something, then negative D also divides it. So the positive one is going to be the bigger one. So yeah, so D does have to be positive because it's the largest. Yeah, good. Okay, so what are the properties of it then? So in other words, we want to say D satisfies the following 2 conditions. The first condition is it needs to be a common divisor. So it needs to satisfy this definition, that it divides both of them, right? D divides A and D divides B. And then the second condition is what? Well, it needs to be the biggest one. So not just positive, but the biggest one of all the divisors. So the way we can say that is we can say that if there's another one that divides both, then what can we say about that? So if C divides A and C divides B, then what can we say about the relative size of C? Less than or equal to B. Yeah, yes, exactly. Yeah, y'all are getting the hang of this. I'm telling you, I was grading homework 6 and I was thinking, okay, y'all are getting it. Y'all are doing really good. So I don't know if you feel like you're doing really good, but from my perspective, you've grown a lot in the last few weeks and I'm really proud of y'all. So there's my little moment. Yeah, so C has to be less than or equal to D. Very good. Okay. So, so the greatest common divisor of A and B is usually denoted like this, A, B, just in parentheses like that. So here's another place in mathematics where we denote things like that look like that. What are all the things that we denote this way? Points in a Cartesian plane, like an ordered pair of points. What else?
Like set.
A set, like an interval. Yeah. And now the GCD. So if you want to be very clear about what you mean, I sometimes write GCD, A, B. And just put the letters GCD in front of it, and that way it's like super clear we're talking about GCDs. Now, on all your homework and stuff, it's just gonna be written this way because we're talking about GCDs, and so it's pretty clear. But sometimes if you're like switching back and forth between notations, it might be nice to write that little GCD in the front just to be extra clear, so. So we'll write this, or you could do that if you're in a situation where you need to be clear. Yeah, so you gotta watch out for that. You know, this kind of thing throws students off all the time. Students even, even college algebra students have a really hard time with like ordered pairs and intervals and like, how do I know what it means, kind of thing. So yeah, so sometimes I like to just write GCD to be clear. Okay. So here's a question. Can you find two numbers A and B, integers, let's say integers, such that the GCD of A and B. So talk to your neighbors and see if you can come up with some numbers that have GCD equal to 1. We'll get a few examples.
Maybe, or yeah, actually, you're right, if A was 1. Yeah. It would carry out to all. Yeah, any two prime numbers, one in any number, and then one.
It can be close.
9 and 28.
All right, what'd you come up
They
with?
don't share anything else in one. But 28
Any examples of numbers that have GCD equal to 1? Austin?
5 and 2.
5 and 2. Okay, so the GCD of 5 and 2 is 1. Okay, any other examples? Yeah, Melissa?
I think 9 and 28.
9 and 28. Okay. What do you guys think? Does that make sense? I mean, to write it out? That has a lot of factors, so. So 9 is just 1, 3, and 9, right? And 28 has what factors? 1, 2, and 14, right? 4 and 7. So you agree? Yeah, no common factors, okay? Some of you are coming up with little conjectures. What are some conjectures you can have?
Is there any two prime numbers?
Any two prime numbers? What do you think? The GCD of, we'll say P1, P2, or P1, P2 are prime, which we haven't defined yet. We'll define in the next section. Yeah,
You said as long as one of them is prime.
as long as one of them is prime. Is that true?
No, because the prime number itself is a factor.
The prime number could be a factor of this number. Yeah. Yeah, so that would work as long as that number, let's say B equals 1,
When they're not equal.
when P1 does not divide B. We could say that. I guess we don't have to call it P1, we can just call it P. And P is prime.
No, it says A is 1.
If A is 1, so the GCD of 1B for any B is 1. Yeah, now those are some nice conjectures. Yeah, good. So now this one's interesting because it doesn't involve any prime numbers, does it? But they just don't have any common factors. And so the what we would say about 9 and 28 is we would say that they're relatively prime or co-prime. And so that means that the numbers don't share any common factors. So this is a definition. A and B. Not both 0. Are co-prime or relatively prime. If the GCD of A and B if it's still going or not. Okay. It says one person is watching now. Does that mean, is that talking about me or is that someone else? I don't know. Okay. Okay, so yeah, so two integers, not both 0, are relatively prime if they have no common factors. And you can see why the relatively prime part comes in, because we were kind of talking about prime numbers having this property. But those numbers are relatively prime to one another. Okay. All right, so here we're going to switch gears for just a second. I'm going to go over here. Okay, and so you're going to have to work in a group on this to see what you can do. So this is going to seem like a really weird shift, but we're working up towards the proof of theorem 1.2, the proof and the statement of theorem 1.2. So here's another activity. So let's say exercise, represent all points on the number line. You don't have to represent all of them, but you can just draw a number line and put them on there as best you can. And then we'll see patterns. That can be written as a linear combination of 6 and 10. So in other words, they can be written like this. So we want the set of all x's such that x is equal to 6u plus 10v. U and v are integers. Okay. So we'll draw our number line. Okay. So 0 is in there. 6 is in there. 10 is in there. And then you can go on from there. Okay, I'm gonna run to the restroom. So work with your groups and see if you can identify all the numbers that you're in linear combinations.
Yeah. Yes.
So I think that's all the even. Oh, I guess not.
All right, what'd you get?
Yeah.
Anyone get 12? 12 in there? 226. What else do we have in there? 16? Okay, what else? 18? How'd you get 18?
Three, use 3 and use 0.
Oh, yeah, 3 times 6.
20.
20? What about some smaller ones? Can we get smaller than 6?
4.
We can get 4. How do we get 4? 10 minus 6? What about, we can get 2? How do we get 2?
10 minus 12, or I guess negative 10 plus 12.
Yeah. Negative 10 plus 12 is 2. Can we get 1? We can?
Oh, no, second.
Oh. Okay. But once we have 2, what can we get then?
8.
We can get 8, yeah, because 6 is 2 plus 8. So once I have something in a linear combination, I can get all of those, right? So I can add, so now that 2 is written as a linear combination of that, I can write 8 as 6 plus 2, and 2 is a linear combination, and so I can go on from there. So once I get, I can also do negatives, right? Yeah, so I'm gonna get all of these. So we're gonna end up with all the even numbers. You see that? Okay. All right, so what's your conjecture if we had 5 and 20? So what if I had this set of all x such that x equal 5u plus 20v? U and v are integers. What do you think? Who's in there? 5? Every multiple of 5? Yeah, because 5 is in there. Can we get anything else? You get 15, 10, 15. Yeah, so any multiple of 5, right? Can I get anything smaller than 5? Don't think so? Why not? Why not?
5 is a multiple of 20.
Yeah, say that in a different way.
So 20 is divisible by 5.
20 is divisible by 5, or 5 divides 20, right? And so if I add or subtract any multiple of 20 from a multiple of 5, I'm not going to get something other than a multiple of 5, right? Because 5 divides that. What if I had 10 and 11? Linear combinations of 10 and 11. It'd be every integer. Why? Well, can we get 1? Yeah, once I get 1, then I have all of them, right? because if 1 is a linear combination, so 1 is equal to 11 minus 10. So once I have that, then I can get every other integer from that. Does that make sense? Yeah. Because I can say 2 is equal to 1 plus 1, which is equal to 11 minus 10 plus 11 minus 10. And so that's the linear combination of 10 and 11. Okay, so you see that? Yeah. So, yeah, so we're gonna get every integer. So what do you think is gonna be true in general here?
Will it be in intervals of their GCD?
In intervals of their GCD? Yeah, I mean, that's what it's gonna end up being, but it's gonna take some time maybe to get there. So you see in all these cases, it ended up being intervals of their GCD. That's what we're gonna prove, okay? So we get, so the GCD of 10 and 11 is 1, they're relatively prime to one another. So we end up getting all the integers, can be written as a linear combination. Here, the GCD was 2, right? When we did 20 and 5, their GCD was 5, right? We got all the multiples of 5, and so on. So, so we're going to read theorem 1.2 in our textbooks. So I'm trying to decide. Okay, I think I want to keep those divised. Well, do I want to keep divised at 12 and 30 up there? I might use them in a minute. Okay, we'll leave them up there. So let's write out the statement of theorem 1.2. So theorem 1.2 says, let A and B be integers, not both 0. And let G be their greatest common divisor. D be their greatest common divisor. Okay. Then there exists not necessarily unique integers U and V such that D equals AU plus BV. So a couple of things we want to caution. So one thing you might notice in there is the not necessarily uniqueness, right? The division algorithm, we got unique Q and R, didn't we? That satisfied those conditions. You don't necessarily get unique integers here. But let's say here, D, if we have D equals AU plus BV, does not imply that D is equal to the GCD. And we know that's true because we have all of these integers are linear combinations, but not all of them are the GCD, right? Yeah. In fact, Brandon had an idea about what is the GCD. So we had all these numbers that were linear combinations, but which one was the GCD?
In the points, I don't know.
Yeah. What's another way to say that?
Would it be the like closest to 0, like the
Yeah, exactly. You can call it the infimum, but we don't have a definition for that yet. But the infimum of the set that's greater than 0 Yeah, so, so yes, it would be that, but we can say the smallest positive one. Yeah, so we'll say note from our exploration. We conjecture that D is the smallest positive integer that can be written as a linear combination. D equals AU plus B. Yeah. So, and in fact, that's what we're going to use in the proof. Okay, is that D is the smallest one. And that should remind you of an axiom, the well ordering axiom, right? Yeah, so if we want to show that something is the smallest positive integer, we first have to come up with a set and then show that it's what? Remember the well ordering axiom? We have to show it's not empty. If it's not empty, it's got a smallest one. That's going to be the one we're going to pick, and then we're going to show that it works. Okay, that's how we're going to prove it. Okay, good. All right. So, yeah. So if we want to show, okay, so you kind of get an idea for the flow of this proof. We're going to make a set of all the numbers that can be written as linear combinations. Then we're going to show that that set is not empty, right? And then we're going to say, okay, let's pick the smallest one by the well ordering axiom. And then we want to show that that smallest one works, right? So that smallest one has to satisfy the definition I erased of GCD, that it has to divide both A and B, and it has to be the smallest one, right? So, so how do we show using the division algorithm that something divides something else? So let me write that down in words so you can see what I'm trying to say here. Let's point this over there. Okay, so how would you use the division algorithm to prove that one number divides another? To prove that, let's say T divides A.
R is equal to 0.
The remainder has to be 0. Yeah, right? So the division algorithm will give you, if T is positive, the division algorithm is that there exists a unique Q and R such that, what is it? I'll give you some time to catch up, and then I want you to write the statement down using the letters we've got. We want to show T divides A. So what does the division algorithm do? Use your T and A and the Q and R put together.
A equals 2Q.
A equals TQ plus R. Oops, why did I write 2? I don't know. TQ plus R, and 0 less than or equal to R less than T. And our goal is we will need to show that what? R is 0. Yeah. If we can show that R is 0, then we have shown that T divides A, right? So that's how we are going to do it in the division algorithm. Okay, we're getting very close. We're getting very close. Okay, so let's go back to the theorem, right? Let's read the theorem again. let A and B be in Z, not both 0, and let D be their greatest common divisor. Then there exists not necessarily unique integers U and B, such that D equals AU plus BB. So we're gonna have to do a few things. First of all, we're gonna have to set up a set, right? And so in this proof, we're gonna set up a set. So if you, well, y'all don't have your textbooks, but, I'll leave that there. So let's talk about this set that we want to set up. Okay, so the set that we want to construct, we're gonna in the proof of theorem 1.2, we will start by defining the set S to be the set of all integers AU plus BB, such that U, V are integers and AU plus BB is positive. It's the set of all positive numbers that can be written as a linear combination of the two. But U and B don't have to be positive, they can be negative. So I have a set presumably of positive integers. To use the ordering axiom, I need to do what? Show that that set is not in, oh shoot. Okay. So we're going to show that set is not empty, right? Yeah, Zach.
What is AU
Or-
plus BB?
Sorry, you're not Zach. You're Jake.
Jake,
Yeah.
Why does AU plus BB have to be greater than 0?
Well, because we want to use the well ordering axiom.
Okay.
We want to use the well ordering. Yeah, we want to use the well ordering axiom. And the well ordering axiom only works for sets of positive integers. Yeah, so that's why. Okay, so yeah, so we need to show that it's not empty. So what is something in that set? Now, A and B could be positive or negative, right? So what's something in that set that's definitely positive? Okay, so if I know that A is any number, positive or negative, what's a positive number I could create out of A? The absolute value of A, but we want it to be in that form, right? So
Where is it?
the square of it,
We have U and T equaling.
yeah, that's what we can do, exactly. So we can write it as A times U is A plus B times V is B. Right? And so that's exactly it. And that is A squared plus B squared. And there may be something we could do with absolute value, but if A is negative, say, and the absolute value of A is positive, then when I multiply them, I still get something negative. So we really do need to square it so that we can get something of that form. So that is equal to A squared plus B squared, which is definitely greater than or equal to 0. And it's of that form, right? Consider that. So A squared plus B squared is contained in the set S. So guess what? Not empty, William?
If it can be equal to 0, it wouldn't be enough.
Oh, you're right. Because in the theorem, A and B are not both 0. Yeah. So, yeah. So since A and B are not both 0, thank you for noticing that. A squared plus B squared is definitely greater than 0. Yeah. Yeah, good catch. Okay. All right, so we found that it's not empty. And so the well ordering axiom says that there must be a smallest one. And what should we call that smallest element? We can call it, in the book, I'll just use what they were doing in the book. They were using T. So let's use T. We'll just, so we can be consistent with the book. It's gonna be the divisor D, but yeah. So let's call him T. So T equals AU plus BV for some U, V, N, Z. And so what's the next step going to be? What are we gonna have to do next? Well, we need to show that T meets the criterion of being the GCD. Okay, so that's what we want to do. So we want to show. Oh, whoops, I skipped something, but anyway, that's fine. We're out of time. So let me just sketch out the next part of the proof, and we'll write the proof in its entirety in the beginning of next class. So, so the next step, well, let's call this step 1. Step 1, we constructed that set and showed it was non-empty. Step 2, we want to show that T divides A and T divides B, and if C divides A and C divides B, then C is less than or equal to T. So that's what we want to show next time. Okay. Okay, and it's time to go. So we'll finish this next time. I got to the end of where I was trying to get today. That never happens. Okay. Yes. Yeah, I'm gonna Zoom with you. Okay. And then Peyton, we're on for right now. Okay. I'm gonna figure out how to stop this from streaming.
I'm just gonna run this back in real quick.
Yeah, of course. Yeah, of course. Okay. So now I want to save it. Okay, and so now I can stop it. Did it save? I have no idea what happened.